multiplication, and basically what this says is if you have a product under the radical, it's the same thing as the radicals of the two factors multiplied together. And it can go two ways. So I have the square root of 2 times the square root of 8, which would give me the square root of 16, which is 4. So this and that are equivalent. So if it makes sense to go from the factors to the product, then you go that way. If it makes more sense to go from a product to the factors, then you go that direction. Cube root of 3 times the cube root of 9 is the cube root of 27, which is 3. So what you cannot do is you can't multiply the cube root of 2 times the square root of 5 and have that equal some root, because this is a cube root, that's a square root, so we can't do this. They have to be the same kind of root. Okay. Now going the other direction, 32 is 16 times 2. And 16 is a perfect square. So I can take out the square root of 16, which is 4. And this 2 is like a remainder. It's going to stay behind. And then if I have an exponent of 8, I divide my exponent by 2 because I have a square root. There's like a little invisible 2 there. And 8 divides by 2 evenly, and that's 4. And so the only thing that's left behind is this 2. Okay, if I have a 4th root, well, 16 is 2 times 8, and 8 is 2 times 4, and 4 is 2 times 2. So I have 4 2's. I'm looking for a set of 4. So I can pull out that 2. Nothing gets left behind on this. I take my exponent and I'm going to divide it by 4 because I've got a 4th root. And so 24 divided by 4 is 6. And then I take this exponent and divide it by 4. And what I get is 3 with a remainder of 1. Right? 4 times 3 is 12, so I have 1 left over. I can pull out the 3, but this remainder of 1, that stays behind. So I have 1b left inside. Alright, so square root 4 times 3, and I know 4 is 2 times 2, so it's a perfect square. So that comes, the 2 comes out, the 3 gets left behind. 6 divided by 2 is 3. 3 divided by 2 is 1 with a remainder of 1. So I can bring out a 2, 3 C's and 1 D, and then 1D gets left behind. This remainder right there gets left behind. So here I've got a cube root, so I'm looking for 3. I've got 3 3's. Divide this 12 by 3, and it equals 4. Divide the 7 by 3, and I get 2 with a remainder of 1. So that 1 is left behind. So I have 3y to the 4th z squared times the cube root of z. Well, we had multiplication, so now we have division. If I have a situation like this where I have the square root of 27 divided by the square root of 3, that's the same thing as the square root of 27 divided by 3, which is the same thing as the square root of 9, which is 3. Okay. So sometimes it makes more sense to put them together under a radical so that you can do the division and then simplify it from there. Other times, like these are together under the radical already, but I can't divide this. So in this case, it makes more sense to split them. I'm going to divide that 6 by 3, so this is x squared, and the cube root of 8 is 2. So here we have square root of x to the 6th over y to the 7th. So I'm going to split that, and I'm going to get x to the 3rd over, actually I'm not going to do that part yet, sorry. I'm going to split that. Okay, big fat rule. We have a lot of rules when it comes to denominators. No zeros in the denominator, no radicals in the denominator, no imaginary numbers in the denominator, no negative exponents. You know, we have like all these rules about what can be. Radicals in the denominator are illegal. So when you get a situation like this, you have to do what's called rationalizing the denominator. Okay, and in order to rationalize the denominator, here I have a square root. Whenever you have a square root, you just multiply it by exactly what you already had. And the reason is because if you square a square root, they cancel each other out. And so you end up with the square root of x to the 6th, y to the 7th over y to the 7th. Now I can take the square root of this and I get x to the 3rd, y to the 3rd, the y remaining, over y to the 7th. And then these y's cancel out 3 of those y's. And so my final answer is x to the 3rd times the square root of y over y to the 4th. Sorry, I ran out of room there. Okay, so square root's really nice. Cube roots, third root, fourth roots, fifth roots, those get a little testy. Okay, so first I'm going to split this. Okay, and here I have a fourth root of 5x. In order to clear out the roots, I need this to be 5 to the 4th, x to the 4th, and then it would cancel, right? So when I multiply this by, if I want 5 to the 4th, I need to add 3 more 5s. If I want x to the 4th, I need to add 3 more x's. Which would give me let's see, hold on one second. I know it's 125, I just don't remember what 125 times 6 is. So I have 125 times 6, so 750. Okay, so you see how I have 5 times 5 to the 3rd gives me 5 to the 4th, and then x times x to the 3rd gives me x to the 4th. And the reason we do that is because these fourths will cancel with this root. And so I'll have the fourth root of 750 x to the 3rd over 5x. And 750, I already know, actually is not going to have any fourth root. And here's why. Because I have 3 5s and then a 6, which is a 2 and a 3. So I don't have 4 of anything. Does that make sense? So I'm done. I don't have to simplify it any further. A couple more. So here I have the square root of b to the 5th. So I can just multiply this by square root again, because square roots cancel each other out. Those are nice and easy. So this will give me the square root of a to the 9th, b to the 5th, over b to the 5th. Square root of a to the 9th is a to the 4th with an a left over, and then I have a b squared with a b left over. Right, because 9 divided by 2, 5 divided by 2. And then these 2 will cancel with 2 of those, leaving me a to the 4th times the square root of ab over b to the 3rd. So here we have a cube root. So I have 4. Now 4 is the same thing as 2 squared, right? So this is actually, I'm going to write that off to the side. So this is actually the cube root of 3 over the cube root of 2 squared y. And the reason I did that is because this way I'm multiplying by a smaller number. I'm not going to have anything to worry about reducing. So I need 3 2's and 3 y's. So in order to get 3 2's and 3 y's, I'm going to add this, or multiply this by 1 more 2 and 2 y's. Make sense? Which would give me the cube root of 6y squared over the cube root of 2 to the 3rd y to the 3rd. This is not going to have any sets of 3 that come out of there. And then the cube root of 2 to the 3rd is just 2y. If you didn't see that 4 was 2 squared, you could have done 4 squared y squared. And what you would have ended up with is the cube root of 12y squared. Sorry, not 12. 48. Because it's 4 squared, so it's 16 times 3, right? So if you had done 4 squared y squared, you would have ended up with the cube root of 48y squared over 4y. And 48 is 8 times 6. And 8 is a perfect cube. So it would have been 2 times the cube root of 6y squared over 4y. And then the 2 and the 4 would reduce. And so you'd end up with same answer. It's just that with finding the 2 squared, we didn't have to do any reducing, any further simplification. Whereas if we used the 4 squared y squared, we would have had to pull out that 8 and then go from there. Simplifying a radical expression. Okay, a radical expression is in simplified form when the index which is whatever n, is as small as possible. Okay, and the index is this number here. What kind of root do you have? Okay, the radicand contains no factors Okay, so the radicand contains no factors that are nth powers of an integer or a polynomial. So, you know, if you factor tree the number, you don't have any matching sets that are the same as n. And the radicand is whatever's right here. Okay. The radicand cannot have any fractions. Okay, so you can't have any fractions under your radical. You can't have fractions in your radical, and you can't have radicals in your denominator. All right, and then that's the next one. No radicals appear in the denominator. So if we have like that, that's a big fat no. And if you have like that, also a big fat no. Okay, so multiplying radicals. We have cube roots. I know those threes are really hard to see, so these are threes right there. Okay, so what you do is you multiply any coefficients. And then you multiply the radicands, that's the stuff underneath. And then you simplify if possible. All right, so those are your steps. Step 1, 2, and 3. Okay, so 5 times 3 is 15. And then I have 12 times 18. Not 12 times 1, 12 times 18, which is negative 216. Now this is a cube root, so I can have negatives. A times a squared is a to the third. B to the fourth times b squared is b to the sixth. Okay. Okay, I'm going to factor 216. And I'm looking for triples because this is a cube root. I have 3 2's and I have 3 3's. Okay, and because this is negative, I'm looking for a negative also. So I could either make the 2 or the 3 negative, it doesn't matter. Oops. And then I have 3, an exponent of 3 here, so, and I'm dividing by 3 because again I'm looking for cubes. Dividing by 3. So I have a, because 3 divided by 3 is just 1, and then b squared. So this is negative 90 ab squared. Okay, next example, square roots. So I'm going to do 6 times 4 is 24. 8 times 2 is 16. C to the third times c is c to the fourth. D to the fifth times d to the third is d to the eighth. Square root of 16 is 4. That's 4 times 4. Divide by 2 and divide by 2. So I get c squared d to the fourth. So this is 96 c squared d to the fourth. When you're adding and subtracting, you treat the radicals like a variable, so they need to match. So the radicals have to match. So the first thing we have to do is simplify them. And then you would collect like terms. So any radicals that matched, you would add them together or subtract them. Bless you. So 98 is 2 times 49, and 49 is 7 times 7. So I can bring out that 7, and I'm left with radical 2. 32 is 2 times 16, and 16 is 4 times 4. So I can bring out that 4. The 2 is already there, so it doesn't go away. And then this 2 right here gets left behind. So this is 7 radical 2 minus 8 radical 2. So that's negative 1, but the 1 is invisible. So I have, that's supposed to be 4 times the square root of 8, not the 4th root of 8. Okay, sorry about that. So 8 is 2 times 4, and 4 is 2 times 2. So this is that 4 that was hanging out. And then 50 is 2 times 25, and 25, of course, is 5 times 5. And I'm just going to add 8 and 15 to get 23. Add and subtract in the same problem. So this one I can bring out 2 2s. Here I can bring out 3 3s. And I have 1, 2, 3 pairs of 2s from 128. So this is 5 times 2 times the square root of 3 plus 2 times 3 times the square root of 3 minus 2 times 2 times 2 times the square root of 2. So I have 10 times the square root of 3 plus 6 times the square root of 3 minus 8 times the square root of 2. I can only add my like terms. So I get 16 times the square root of 3 minus 8 times the square root of 2, and I can't go any further. Expressions. You've seen stuff that looks like this before. They had x's and numbers in them. We're going to go back to our good friend FOIL. So we're going to do first, and then the outside, and then the inside, and then the last. So first, and then outside, and then inside, and then last. So for first, I'm going to get 4 times the square root of 3 times 3 times the square root of 2 plus 4 times the square root of 3 times negative 6 plus 5 times the square root of 2 times 3 times the square root of 2, and then plus 5 times the square root of 2 times negative 6. Okay, that's all the multiplication. So first, and then these are the outside, those are the inside, those are the last. So this is going to give me 12 times the square root of 6. And then that's going to be minus 24 times the square root of 3. This is going to be plus 15 times the square root of 2. And then here I'm going to get minus 30 times the square root of 2. Sorry, square root of 4. one erase? Forgot to multiply my 2's. Sorry, that's the square root of 4. This can't be simplified. This can't be simplified, but this can. Right? The square root of 4 is 2. So the square root of 4 is 2, so that's 30. And I have no like terms, so I'm done. Okay, so I'm going to do first. I'll use color on this one. And then outside. And then inside. And then last. Okay. Okay, then we just look at each of these. 15 has no squares in it. 6 has no squares in it. Neither does 5, neither does 2. I can't do anything with any of that, so I'm done. I don't have like terms. I can't make them into like terms, so it's just finished. Now, conjugates. Remember we had complex conjugates? Where it was a plus bi, a minus bi. This is, if I have a plus b, the conjugate of a plus b is a minus b. This first a, it doesn't matter if a is positive or negative. That doesn't change. The only thing that changes is the sign on the b. Okay? So if I want to rationalize this denominator, before if it was just a square root of 5 in the denominator, I'd multiply by square root of 5. But here if I multiply by square root of 5, sure, that'll go away, but then I just have another square root of 5. It doesn't work. And I can't have any radicals in the denominator, so to get rid of radicals in the denominator, I'm going to multiply by the conjugate. So if this is minus, this is plus. For my numerator, I'm just going to distribute. So I get 2 times the square root of 5 plus 2. And then in my denominator, when you FOIL everything out, if I do first, outside, inside, last, what I end up is with is this. I end up with the square root of 5 times the square root of 5 plus the square root of 5 minus the square root of 5 minus 1. So this is 5. These cancel. Right, negative, positive, and then I get minus 1, so that's 4. So a shortcut, if you're using conjugates, is you can just multiply, instead of multiplying first, outside, inside, last, you can just multiply first and last with conjugates only. Because the outside, inside will cancel each other out, because that's the whole point of using this plus minus. And so you'd have gotten 5 minus 1, so you get 4. Now all 3 of these would have to be able to be reduced in order to reduce this, and in this case they all divide by 2. So I get the square root of 5 plus 1 over 2. Here I have the square root of 3 plus 6, so what I'm going to multiply by is the square root of 3 minus 6. In this example, I'm going to have to FOIL the top, the numerators, because I have 2 But again, shortcut, I can just do first and last in the denominator. So if I FOIL the numerator, I'm going to get 9 times the square root of 3 minus 54 minus 2 times 3 plus 12 times the square root of 3. That's the first, outside, inside, last. And in my denominator, I'm going to get 3 minus 36. So here I have negative 54, negative 6, so that's going to be negative 60. And then 9 plus 12 is 21. And then 3 minus 36 is negative 33. All three of these will divide by negative 3, which is going to give me positive 20 minus 7 times the square root of 3 over 11. One more. I have 2 radicals. Doesn't matter. It's the same exact process. I'm going to multiply by the square root of 3 plus the square root of 2. So I'm going to end up with the square root of 18 plus the square root of 12. That's multiplying up top. And in the denominator, 3 minus 2, right? Because I do first and last. So my numerator, 18 is 2 times 9, and 12 is 3 times 4. And that's 1, so that's just going to go away. And I can take my 3 out from the 9 and my 4 out from the, or the 2 out from the 4, and I get 3 plus the square root of 2, or 3 times the square root of 2 plus 2 times the square root of 3. Okay, so for our next section we have rational exponents. Okay, and remember, rational numbers are fractions. Okay, so basically this is exponents as a fraction. Okay, so if you have basically any radical, if I have something like this, the nth root of a to the b. Okay. This number would be the numerator of the fraction. And this number would be the denominator of the fraction. So the nth root of a to the b is the same thing as a to the b over n. So just as an example, if I have the x to the 1/6, that's the 6th root of x to the 1, which is just the same thing as the 6th root of x. If I have, the 4th root of z, well, there's that invisible 1 right there, which is my numerator, so this is the same thing as z to the 1/4. To evaluate these. All right, if I have 81 to the negative 3/4, okay, first of all, I can't have negative exponents, right? So whenever I have a negative exponent, I have to turn it into a denominator. Then 81 to the 3/4, that doesn't mean anything necessarily. But I know that this is going to be my root and this is my exponent. So that's the same thing as 1 over the 4th root. That's really unattractive. The 4th root of 81 to the 3rd. Okay. All right. So now I'm not going to multiply this out. I'm not going to multiply 81 times 81 times 81 to try to figure out then the 4th root of whatever giant number that is. That doesn't make any sense, does it? So what I am going to do though is 81 to the 3rd is this. I have 4 9s right here, so I can pull out a 9, and then I just want to see, look at that, I have 4 3s, so I can pull out a 3. Right, so 81 to the 3rd has 4 9s and 4 3s. So this is equal to 1 over 9 times 3, so it's 1 over 27. Let's try 216 to the 2/3. Okay, this is the same as the cube root of 216 squared. And again, I'm not going to square 216 and then try to factor that giant number. I'm just going to factor it twice. It's just easier that way. So I have 2 sets of 2s and 2 sets of 3s. So what this equals is 2 times 2 times 3 times 3, which is 4 times 9, which is 36. Now, there's another way to do this. And that involves factoring 216 first, you know, et cetera, and we know that that factors to 2 times 2 times 2, 3 times 3 times 3. So it actually factors to 6 to the 3rd to the 2/3. Right, because it's 2 to the 3rd and 3 to the 3rd. So it's the same thing as 6 to the 3rd. And if you take a power to a power, you multiply the exponents, and then if you multiply fractions, they cancel, which gives you 6 squared, which is 36. So 2 ways to go about this. If you have a number here that you know is a square or a cube, it's really easy, a lot easier than factoring it. But either way, as you can see, we get to the exact same answer. So it doesn't matter. Okay, so another thing that we have is if I have, let's say, some base b to the exponent of xy. And we've already talked about how that's the same thing as the y root of b to the x, like this. It's also the same thing as the y root of b raised to the power of x. And sometimes that's much easier to do. So if we take that 216 example that we just had, that's the cube root of 216 squared. Well, the cube root of 216, if we, factor it all out, it ends up being 6. Like, we factored it on the last page. So if you factor it all out, it ends up being 6. So it becomes 6 squared, 36. So sometimes this is actually easier if you have a perfect square, perfect cube, something like that. If I do 27 to the 2/3, well, I know 27 is a cube. So that's 3 squared, so it's 9. It's easier than squaring 27 and then trying to take the cube of that. I take the cube of 27 and then I square it. Okay. If I have the same base with two fractional exponents, I add them together. Well, in order to add fractions, I need a common denominator. In this case, my common denominator is going to be 15, so I'm going to multiply by 3 here and by 5 there. And so I'm going to get x to the 10/15 plus 3/15. So this is x to the 13/15. Okay. P to the 1/4 times P to the 9/4. These already have a common denominator, so I'm just going to add them. And this will reduce. So you treat the fractional exponents just the same way you would treat any normal fraction. Reduce them if you can. We don't like to have fractional exponents in the denominator. So let's say I have a negative fractional exponent and I have a base that's just a letter. It's not a number. I can't clear it. This is going to be 1 over b to the 5/6, which, if you remember, we can't have radicals in the denominator. Just like you can't have radicals in the denominator, there's no fractional exponents in the denominator. So I need to get rid of this 5/6. Now, to do that, I'm going to turn it into a 1. Right? If I have an exponent of 1, it's not a fraction anymore. And since I'm adding, I want to make this 6/6. So I'm going to multiply by b to the 1/6. And the reason I do that is because this ends up being b to the 1/6 over b to the 6/6. That's very difficult to say. Which is b to the 1/6 over b. and I don't reduce this because this fractional exponent, that's like a radical and this isn't. So that's my answer. Because if I did try to reduce it, it would end up getting me back here anyway. So I have r to the negative 3/5. That's the same thing as 1 over r to the 3/5. But I can't have fractional exponents, so I need to turn this into 5/5. So in order to turn that into a 5, I need to multiply it by 2/5. So now I have 5/5 because I add them together. So then that becomes r to the 2/5 over r. Now, does anybody see a shortcut? At all? All right, shortcut. Let's look at that example we just had. I had r to the negative 3/5, right? I want to find out what to make it equal to 1, right? Take that and put it over one of them. So if I had x to the negative 4/7, to turn this into a 1 is going to be 3/7, right? Because 4 plus 3 is 7. Does that make sense? So it's just a shortcut. You don't have to do all the multiplication. But you understand why this becomes this now. Spend all that time showing you how to rationalize the denominator and get rid of the radicals in the denominator. Well, sometimes there's another way to go about it. Okay? If I turn these into fractions, not 1/2. Yeah, 1/2. So I have the 4th root of 27, so that's 27 to the 1/4. And the square root of 3 is 3 to the 1/2. Right? Because if I multiply this by the square root of 3 over the square root of 3, I can get rid of the denominator that way, but it's not gonna, I can't combine these because they're different radicals. So when that happens, now 27, I have this 3 here. I want to put this in terms of 3. And 27 is 3 to the 3rd. And that's to the 1/4. Okay. And the reason I want to do that is because now I'm going to have a common base. So this is 3 to the 3/4 over 3 to the 1/2. And when I have two exponents, common base, numerator, denominator, if I'm multiplying them, I add. If I'm dividing them, I subtract. So I common denominator, subtract them, and then convert it back into a radical. Do one more. Okay, so this is 32 to the 1/4, and this is 2 to the 1/3. I'm going to put 32 in terms of 2. And if you didn't know that, you could factor it. You could make a factor tree and you'd get 5 2s. Multiply these, and so you get 2 to the 5/4 over 2 to the 1/3. So that's 5/4 minus 1/3. My common denominator between a 4 and a 3 is 12. So that's 2 to the 15 twelfths minus 4 twelfths. So that is 2 to the 11 twelfths, which is the 12th root of 2 to the 11th. Conjugates, I have the conjugate of this is going to be 3x to the 1/2 minus 2. So it's the same idea as what you've been doing. So if I FOIL this out, I get 3x to the 2/2, right? Because a half plus a half is 2/2. Minus 2x to the 1/2 minus 6x to the 1/2 plus 4. And when I do the denominator again, because I'm just doing conjugates, I only do first and last. So I get 9x to the 2/2 minus 4. Okay, I'm going to combine my like terms here. First of all, 2/2 is just 1. So that goes away. I have -2, -6, so that's -8 to the 1/2 plus 4 over 9x minus 4. And this is done.